All right, let's go ahead and get started. I do want to welcome you back to Unit 7. This is chemical reactions. And I'd like to spend a little bit more time on double replacement reactions and rethink some of the material that we went over last time, just to make sure we solidify this in our head. So here we go. So we said that to determine the products of a double replacement reaction, you combine the cation of one reactant and the anion of the other, and do the same thing with the other two reactants. So here we have the reactants of a double replacement reaction. We have lead nitrate and potassium iodide. Now, just a couple of things of note, and that is, first of all, I want to determine what the charge is on this lead atom, because lead is a transition metal. That means it has multiple oxidation possibilities, multiple charge possibilities, okay? So NO3, remember, has a charge of -1. And because of that, and the fact that there are two of them, that must mean that lead must have had a charge of +2. Right? So the charge on the lead is a +2. Now, that charge is going to stay +2 when I move it to the other side. So when lead becomes a product in its new product form, together with another anion, not NO3, but iodide, then it's going to have the same charge as it did before, right? So I just wanted to point that out to start with. So it says both reactants contain a cation and an anion. So this is obviously a double replacement reaction. They're going to be aqueous in both cases. But what are the products, right? What are the products? Now, take the Pb2+. We've already talked about why there's a superscript of +2, why that charge is +2. It's to balance the two NO3 -1s from the first reactant and the I- anion from the second, and combine them to form Pbi2, lead iodide. All right. So remember that we're going to rebalance electronically. In other words, iodine has a charge of -1, but there's two of them because lead has a charge of +2. We started with +2, we end with +2 on the product side. So one of our products is going to be lead iodide. Now, we need to check the solubility chart to see if it's aqueous or if it's insoluble. So let's go to the charts now, okay? So when I look at the solubility chart, I'm going to be looking for iodide, I-, right? I'm going to be looking for I- because that's the anion. It's under the soluble category. Soluble compounds contain, it's the second one from the end. The I- is the second one from the last one. And I'm going to check to see if the thing that it's going to be associated with, in this case it's lead, is an exception to the rule of iodides being soluble. So here are the exceptions. The common exceptions include silver. No, it's not associated with silver. Lead 2+. That's it. Yeah, it is an exception. No doubt about that. So that means what? Iodide ions paired with lead as a cation is insoluble. It's insoluble. It's a solid, right? It's one of the exceptions to the rule of iodides being soluble. Now, since there is at least one reactant, which is a solid, the reaction is going to proceed. So we just tested the first one, the lead iodide, but we now know it's a solid. This reaction is going to go, right? Now, the other reactant that's formed is K+1, right? The other reactant is formed from K+1 and NO3 -1, right? So it is KNO3. So we're going to put these together. The potassium with a charge of +1 and the nitrate with a charge of -1. We get this now, potassium nitrate. Now, from the solubility chart, nitrates paired with potassium are soluble. So remember, all nitrates are soluble. There are no exceptions. So it's aqueous, but that's okay because we've already determined that one of them is a solid. So let's complete the balance the double replacement reaction. We had lead nitrate together with potassium iodide, right? Together with potassium iodide. They're both aqueous, gives us lead iodide, right? PbI2. Why I2? Again, the lead was +2 because it was +2 over here. It's +2 over here. So that means we're going to have a subscript of 2 right there. We said that was a solid. We looked it up, remember? And potassium nitrate, +1, -1, they balance. You don't need any subscripts here, okay? Other than the 3 from the NO3, right? Now, and we said that was aqueous. Now let's balance the whole thing. One lead on the right-hand side, one lead on the left-hand side. I'm going to keep the nitrates together, right? So 2 nitrates right here, because there's a 2 right there, 2 nitrates right there, right? The next one is potassium. 2 potassiums here, 2 potassiums there. 2 iodides here, 2 iodides there. This reaction, this double replacement reaction is going to go, first of all, because of the solid, but it's also balanced for us now. Okay, both electronically and with regard to mass, everything is balanced. All right, let's move on. I want to go back to the idea of conservation of mass. Right? We've talked about this before, but we talked about it at the atomic level and the balancing of chemical reactions based on the conservation of mass. We said that matter couldn't be created or destroyed at the atomic level. That's why we balance chemical reactions. But I want to talk about it at the macroscopic level now. Now, conservation of mass. According to the conservation of mass, matter can't be created, remember, and it can't be destroyed. Now, this means that the total mass on the left and the right hand side of a reaction must be the same, right? So let's take a look at this example, right, from a macroscopic point of view. Let's take a look at this experimental procedure here. So we've got some type of a flask, right? We've got a flask that's stoppered, and inside the flask we have a chemical on the inside of this test tube. It's calcium chloride, and we've got another chemical on the outside. We've got sodium sulfate solution. Now let's take a look at what the scale says. It says 300.23 grams. But now what we're going to do is we're going to invert the flask. Right? It's stoppered, so the liquid's not going to fall out, but the two chemicals are going to mix. The calcium chloride and the sodium sulfate are going to come together. They're going to mix, right? Now what I'm going to do is I'm just going to lay the apparatus back down. Notice what was in the test tube before is no longer in the test tube. It's one complete mixture. What is the total? It was 300.23 grams. Now the scale says exactly the same, 300.23 grams. But notice now that we have a new compound. In fact, CaSO4 is a precipitate in an NaCl solution, right? So what's happening here? Why is it the same? Well, it's because of conservation of matter, conservation of mass. In other words, matter can't be created, it can't be destroyed. In the above reaction, calcium chloride and sodium sulfate, Na2SO4, are measured separately and have a total mass before they react of 300.23 grams. Now, after the closed flask is inverted and the chemicals react, notice that the mass of the resulting CaSO4 and the NaCl solution has exactly the same mass. Even though a reaction occurs, the total mass on the reactants and the product side remains the same. What's the lesson of this story? Well, the lesson is that at the atomic level, when you have a chemical reaction, matter is not created and matter is not destroyed, and therefore in the reaction you must balance atoms. But at the macroscopic level, we're not talking about atoms now, we're talking about solutions, we're talking about flasks and beakers and test tubes and things like that. You see exactly the same thing. That even if there is a reaction and something new is formed, the amount of material doesn't change. If you start with 300.23 grams of material of one type, you're going to end up with 300.23 grams of material of a separate type. Okay? And that's it. Let's take a look at this other problem. In this problem, we've got calcium. In fact, we've got 64 grams of it, and we've got zinc carbonate, 192 grams of it, right? This is an aqueous solution. And what we're going to do is we're going to put these together, and we're going to get this. We're going to get calcium carbonate and zinc. But we want to know how much zinc. That's the question. How much zinc are we going to get? Well, we're going to use our knowledge now of conservation of matter. What do we know? We know that the amount of matter on the left side of the reaction has to be equal to the matter on the right-hand side of the reaction, right? So in this single replacement reaction, and that's what we've got here, we've got calcium replacing zinc. How much zinc is produced? How much of this do we get? Well, we know that 64 and 192 is equal to 256 grams. So that's total mass on the left-hand side of this equation. So 256 grams must be on the right side of the equation as well. Now, calcium carbonate accounts for 152 grams, So the remainder, 256 grams minus 152 grams, must be the mass of the zinc. The zinc must weigh 104 grams. That's conservation of mass. That's what it means. Conservation of matter means that the total amount of material on the left has to equal to the total amount of material on the right. Okay, so we did a simple subtraction experiment to be able to determine that. All right, folks, we're going to move on now. I want to talk a little bit on this particular screencast about diatomic elements and a way to remember what they are. They've come up from at various times in our chemical reactions, and I want to just talk about how to remember what they are. So diatomic elements, when writing reactions, it's important to remember that some elements are diatomic. This means they appear in pairs. We've seen it before. We saw it, for example, with the combustion reaction. Remember when we said that the hydrocarbon reacted with O2 gas, and we said that the O2 gas was diatomic, right? O2 is always, oxygen is always paired with another oxygen. So how can we remember what the diatomic elements are? Well, we're going to use a little mnemonic, and the mnemonic is this: Brinkelhoff. I don't know what that. I mean, it's not a word. You just have to remember that kind of mnemonic. Brinkelhoff. B-R-I-N-C-L-H-O-F. Brinkelhoff. What that means is that the elements bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, those are all diatomic. Whoops, forgot a 2 right there. Let me put that in. All right, those are all diatomic, right? Those are all diatomic. So you're not going to see bromine or iodine or nitrogen or chlorine or any of those by themselves, right? They're going to be diatomic. So Brinkelhoff is going to help us to remember that, right? Brinkelhoff. So from this point on, if I just say, for example, on a test or a quiz, if I say methane, which is CH4, reacts with oxygen gas, you should know that oxygen is diatomic, right? Automatic. I shouldn't have to say reacts with diatomic oxygen. I should be able to just say reacts with oxygen, and that's it. You got it. It's oxygen, it's O2, because it's diatomic, right? Brinkelhoff. All right, I want to talk a little bit about rates of chemical reactions now and what makes a reaction go faster than another reaction. All right, so how do we make reactions go faster, right? How do we increase the rate of a reaction? Well, the first thing we can do is we can heat up the reaction. This increases the kinetic energy. So when you think of chemical reactions, right? You think of particles colliding into each other. That's what a chemical reaction really is. Particles colliding, bonds being broken, bonds being made, right? So if you heat it up, you increase the kinetic energy and therefore increase the speed of the reaction. The second way that you can increase the rate of reaction is by increasing the concentrations. Well, that makes sense. The more things that bump into each other, the greater the chance of a collision being successful and a reactant becoming a product, right? So increasing the concentrations of reactant would be the second one. 3, increasing the surface area, as in, for example, crushing the reactants. Increasing the surface area would crush, or crushing the reactants would speed up the rate of the reaction. All right. The next is stirring, right? Stirring. That's just another way to say that is agitating the solution. You're increasing the collisions between those particles on the reactant side, and that's going to increase the rate of the reaction. And finally, adding something called a catalyst, right? We'll talk a lot more about catalysts later when we talk about reaction kinetics. But a catalyst essentially does this. It lowers the energy of activation. So we'll talk a lot more about this later, but it lowers the energy of activation. It lowers the threshold, in other words, that must be overcome in order for a reaction to work. All right? Folks, I think this is a good place to stop. We'll go ahead and pick this up next time with how catalysts work. So I'll see you in the next one. Thanks. Bye-bye.